Okay. Okay. All right. Good afternoon, everyone. So I'm Keisha Rogers, for those who may not know me, and welcome to the LaRouche PAC discussion for today, March 4th. And I just actually got off a very profound discussion where I was addressing along with LaRouche's, the director of the LaRouche Schiller Institute organization, Chorus, and John Segerson, excuse me. I'm trying to catch my voice, so I just kind of ran in here, so you guys forgive me for a second here. And the nature of just the discussion is the great potential that we have in front of us right now, and just really what we have to be thinking about bringing into existence and creating. And I have a couple of things I want to go through, because you have to look at the fact that we're now at a point where the unprecedented direction that has been brought into motion, that the empire, the British Empire, and what it represents against the progress of mankind is now on the verge of being brought down. And that's really how you have to look at these threats and these attacks that you see coming out against, that are absolutely just disgusting and abysmal. A direct attack coming from a former president of the United States, Barack Obama, on the sitting president of the United States now. And there's been, and then why are these attacks happening? And you look at the fact that it was really only a day or two after the current sitting president, Trump, announced and made clear that it was former President Obama that was orchestrating these demonstrations and these direct attacks on the White House and on the president himself, and orchestrating and fabricating these lies around the whole idea that there was prior relationships between Trump and Russia, Russian President Putin, and people within the Trump administration. And we had a discussion with Mr. and Mrs. LaRouche, and you really have to take this whole fight and look at where it's coming from and how it has completely exploded out of control. I don't know if people might have seen that in the Daily Mail, there was a direct article in the Daily Mail where a close friend of former President Barack Obama made it clear that Obama is committed to leading the fight to make sure that Trump is forced out by resignation or impeachment. You have the continued escalation of threats, including assassination threats to the current president's life, President Trump. And this is coming directly from London, from the British Empire. You have reports that have come out from in France, detailing exactly that the president should be removed or impeached, and what would be the implications for the president being taken out. I mean, you just have this. Where is this coming from? You have a situation where this escalation, what happened on March 1st, really details the intention and the threat. March 1st, in the New York Times, there was an article that came out with the headline, "Obama administration rushed to preserve intelligence of Russian election hack. Some in Obama administration fear that intelligence about Russian interference in the 2016 election could be covered up or destroyed." And it goes on to discuss how that the people within the Obama administration, in the last days of his administration, some White House officials scrambled to spread information about possible contacts between associates of President Donald Trump in Russia and the Russian government. And it just goes on to discuss really what could be looked at as a direct, intentional, orchestrated attack, because this was going on before Trump was elected president, in the oncoming of the presidency within the final days of the election. And you see that this whole idea that you had all of these, from Lindsey Graham and John McCain, these warmongers who wanted to keep pushing this threat of war that has been ongoing, that you had on the Republican and Democratic side, people were coming out nonstop calling for the continued escalation against this presidency. And you really have to look at it from the standpoint of what the potential that was represented in the State of the Union address, where President Trump discussed the question of looking at the actual future orientation, looking at the role of how do we actually bring into existence in the next 9 years, on the 250th anniversary of this nation, a future for the next generations, that we're going to have a new set of, really emphasizing the potential of a new set of relations between nations, that the idea that what had been represented by the former president, the policies of the past 10 years, of the past decades, will not be continued. That's a threat directly to the empire. Now, if we're going to actually realize that potential, then we have to be very honest about where this threat is coming from, what it is that Wall Street, the British Empire, and Barack Obama, and those who have served in that interest, are completely freaked out by. And it's really what we have, and the Lyndon LaRouche and the LaRouche movement has continued to bring into existence, and which was recognized in a very profound article that continues to come up by a collaborator and associate or a friend of the LaRouches, by former Tunisian diplomat by the name of Dr. Ahmed Khadidi. And he really emphasized the true underlying principle of the fight at hand, and the fact that his statement article starts with the title, "The Dream of American Politician Lyndon LaRouche Becomes True 1/3 of a Century Later." And as he emphasizes the importance of the strategic intervention and events that took place recently with Russian Foreign Minister Lavrov, calling for the creation of a new world order to replace the old existing system, replacing the dead transatlantic system. You know, the fact that you had President Trump describing the problems with the transatlantic system from the standpoint of NATO and the continued threats of war. But what he really developed and focused on was the role of Lyndon LaRouche, the American thinker and politician and economist, who was an advisor to President Reagan and what he called the father of Star Wars, a strategic defense initiative. And that LaRouche has been a fighter nonstop, who has continued to expose the role of the collapsing transatlantic system, and that has warned about the onrushing collapse of the international financial and monetary system. And so he also, the writer, author, Mr. Kadidi, Dr. Kadidi, also emphasizes that Lyndon LaRouche was also the only one who prescribed the remedy more than a third of a century ago through a unique vision and capability to foresee the future and avoid the approaching crisis. And I think that that is absolutely appropriate to understand how close we are to bringing down this existing system and to actually bringing forth the vision of Lyndon LaRouche, which the enemies of mankind are absolutely bent on seeing not be brought into existence. And so I think that now, as we look at the escalated fight that Mr. and Mrs. LaRouche has called for, that what we're seeing with the potential from the Trump presidency right now is not a yes, no, or process, or yes, no, for, against, but it's really, you have to look at it from a standpoint of what we're creating and a process and understanding the enemy, and that you have to bring down and destroy that enemy. And so when you look at what we have continued to fight with, to bring into existence around Lyndon LaRouche's unique 4 laws, that these 4 laws are absolutely crucial as an underlying direct policy orientation that cannot be underestimated or that must immediately be adopted. And I will just say that we have a new petition, and we are in a full-scale campaign right now where the petition for implementing the 4 laws, not an option, but an urgent necessity, are more important now than ever. And they have to be looked at from the standpoint that we're now talking about how do we actually implement what's necessary as policy in the United States to bring the United States into alliance with a new system of relations among nations and win-win cooperation, as has been expressed and has been offered by China, and working with China, Russia, and other nations. So let me just, for a second here, just so people have a sense of this, read the new petition, at least the format of the new petition here, where it says, to President Trump and the 115th Congress, pass and implement LaRouche's 4 laws for economic recovery. Join the United States in China's New Silk Road program for global win-win economic development. We, the undersigned, recognize that the transatlantic financial system is on the verge of a new blowout, worse than that of 2007-2008. The conditions of life for the vast majority of Americans have been steadily collapsing over the past 2 decades. U.S. economic policy has focused on protecting Wall Street's speculative bubble instead of protecting the general welfare and future prosperity of the American people. We recognize that emergency action is now needed to preempt a new financial crisis and to put Americans back to work rebuilding our nation and our future. To accomplish this, we asked President Donald Trump and the 115th Congress to pass and implement LaRouche's 4 laws program for economic recovery on an emergency basis, and to join China's New Silk Road program for global cooperation in large-scale infrastructure projects and economic development. The 4 laws define a coherent economic recovery program rooted in the American system of economics. 1, reinstate Franklin Roosevelt's original Glass-Steagall law. separating commercial lending activities from Wall Street speculation. 2, return to a Hamiltonian system of national banking. 3, federal credit to projects and initiatives which create rising levels of productivity and incomes. 4, launch a crash program for the development of fusion power and the rapid expansion of our space program. The American economic recovery will be greatly accelerated if the United States joins the global infrastructure and economic development renaissance flowing from China's New Silk Road program. If people remember the former petition we had, this really has elevated, taken the direction of LaRouche's 4 laws to another level, that we're not going to be able to do this without a new system of cooperation and relations among nations. And it's not just about the United States, but if the United States is going to actually become what was represented in President Trump's speech, we have to actually have a new conception and thinking about, one, that you cannot bring that into existence under the current existing system, that you have to rid of the entirety of this, the failed monetary financial system immediately now, that we have to immediately bring into existence a system of economic credit. So, and based on the foundations of our nation under First Treasury Secretary Alexander Hamilton, which Lyndon LaRouche says his 4 laws are directly derived from. So I think as we get into the discussion with Joel here, one thing we're going to make very clear and continue to make clear in the course of the series of economics classes on LaRouche's economics, based on a principled writing that he did, So You Wish to Learn All About Economics, and based on a continuation of developing the underlying principles governing LaRouche's 4 laws, that this is absolutely critical to understand at this moment, that if we're going to accomplish these goals of setting into motion for the United States a direct policy on reorganizing the economy, it cannot be done under any circumstances except for what Lyndon LaRouche has laid out directly in these 4 laws. And so we have to, as we've been doing, I think there'll probably be some reports coming up pretty soon. I encourage people to do so, because we've already started the campaign for the National Week of Action to escalate around the LaRouche's 4 laws and bringing the United States into the New Silk Road. And that today there was a report from our associates in Manhattan in New York, where they went to first of all, just to let people know, there's pro-Trump rallies going on across the country right now, and we have several of our organizers there. And that one of the rallies in the New York area that we went to had so many different people there. They even had Chinese Americans for Trump. Oh. And they had shirts on, Chinese for Trump, and they said, we have to stop these wars. This cannot continue to exist. We have to work together and cooperate together. And so, I mean, you see the potential is so great right now. And, you know, one of Diane Sayer was, I haven't gotten the report back yet, but was invited to address one of these meetings, because the whole idea that you're just going to have various demographics and people for Trump is the point that the organizers made is we need more. That's not enough. We need to say, what are these people going to actually fight for? How are they going to actually organize this presidency to realize the solutions that have to be brought into existence? And Glass-Steagall and the 4 laws, they wanted us to come in and to actually present that to the participants at this event. So we're doing the same thing across the city right now, across the country right now, and we'll have some more updates and reports. But I would just encourage people, and we'll come back to this, to think of everything you can do in this next week in terms of escalating this fight. We will be planning more rallies in the next week. We want you to call your Congress member, call your state representative. We want you to push these 4 laws and the fact that we have to remove this opposition out of the way, because they want to make sure Obama moving into Washington, D.C. with Valerie Jarrett right near the White House, so he can make it his #1 prerogative to bring down this presidency. And Joe can tell you, I actually reported this on the other discussion about the discussion he had with the Congress member, a woman here, who said, we don't need to be worried about Glass-Steagall and 4 laws and these things. We need to be worried about impeaching Trump. I mean, this stuff is just out of control right now. So
forget a budget or anything.
Yeah, yeah. So I'm going to leave it at that, and we can come back to other reports and discussions that people have concerning how to escalate around this fight, this initiative, and the campaign. This is a full-out campaign that we have now underway, and it is the potential that this is a moment that is unprecedented, that the enemy can once and for all be brought down, and we can have a real optimistic future for the nation if we do our job. So
one real quick question.
Yeah.
Any word on the new pamphlet, when it's going to be available?
So Belinda's asking about a new pamphlet here. The pamphlet is going to be for the upgraded pamphlet of the U.S. joining the New Silk Road. I understand that it is now in the final phases and at layout stage, and so it should be available sometime soon. Right now, we're going to have this pamphlet produced. It encompasses LaRouche's 4 laws and what is required for the United States to join with China and the Silk Road. But it's going to be probably in the next couple of days. I can't give an exact date right now because I don't know, on the website for sure. And it's going to be a PDF or electronic version. And we definitely, this is something with the 4 laws petition, along with the new pamphlet publication coming out, that we need to have as a single package. And we want to print those. We do want to print them. So we need people to really come forward and support this mobilization and contribute to make sure that we have the resources needed to print 1 million of those pamphlets. I mean, just think about, wow, the power, the impact that would have. So we want to get those out throughout the community, businesses, to the international community, everywhere we can across the country. So as soon as we know, but in the meantime, make sure that we can move forward with that process.
I think it's on PDF form already.
You seen it?
No, I thought it was.
No, they were saying they were working on it.
I think they're still working on it right now.
Right.
Okay, so I'm going to invite my friend Joel to come up here, who is going to expound on how we bring this perspective from LaRouche's understanding into being. Okay, here you are. You want to stand behind here? Or?
Here's fine. Any word on whether Kislyak was at the Trump rally? My favorite ambassador. I want to go back to the isoparametric theorem, which we covered a few weeks ago from LaRouche's So You Wish to Know About Economics book. And from there, construct the unit circle and then go to the complex domain. And then from there onto the self-similar spiral action in the conic section. And then on how we go from there to thermonuclear fusion.
All right.
And, I'll try to do that in the next 30 minutes.
All right.
Do you have a plan to get us back to?
Well, no, once you go thermonuclear, that's it. Now, is this blank?
Yes.
Yes.
Okay. Now, first, you remember the isoparametric theorem states that for a minimum perimeter, you get a maximum area. So I'll just construct an example of that. Oh, I'm not blocking you here. But
You got it, okay.
yeah, got it. Okay, it's probably not a perfect circle, but if so, for the minimum circular action, the minimum perimeter, you get the maximum area, which is the circle. Now, this goes back to Nicholas of Cusa, in the 15th century, right before the Renaissance. What LaRouche brings up repeatedly in his textbook is Gauss and Riemann. Now, Gauss takes the unit circle. Now, the unit, the radius is 1. And what Gauss does is he has the diameter. Is that about halfway?
Yes.
Very good.
Okay. So if we have a radius of 1, unit 1, so from the center of the circle to the circumference is 1. And in the opposite direction, you have -1. Now, if you go along the number line from 0, 1, 2, you can go up to all the way to infinity. And the same in this direction, 0, -1, all the way to infinity. Now, what Gauss demonstrates is that this is the simple number line. In the x-axis, if you go up the y-axis, and if you take the arithmetic mean of the x-axis, the number line, in other words, 1 plus -1 over 2, you get back to 0. But if you take the geometric mean, which is -1 times 1, the square root of that, what you get is called the imaginary number, or square root of -1. And in the bottom direction, you get minus the square root of -1. Now, what's the big deal of that? If you look at something you see every day, which is electromagnetic radiation. Now, electromagnetic radiation is not just a simple wave. Now I've shown this before. Light ray.
All right.
That with this circle, what you have, and I want to go back to just some basics. What you have with every circle is the circumference C over the diameter is equal to pi. Now, this is true for a unit circle, it's true for something with the diameter of the Earth, it's true for every circle.
Could you repeat that one more time?
For every circle, if you take this circumference of your circle, your perimeter, and you divide it by the diameter, or twice the radius, for every circle in the entire universe, you get a transcendental constant, a transcendental number called pi. That's the Greek letter pi,
Right.
which is equal to a little bit more than 3, 145, 9, 3.14159. It goes on forever. Now, the 3.14 happens to be Einstein's birthday. So you hear this number, this is Einstein pi day. Now, the other thing, I won't go too much into it, but if you have pi times e, you get pi, and I was promised at the end either a pecan pie, apple pie, or I'll even take a cherry pie. This is for later.
You gotta get a pie in the face.
I have to get my shield on. So now, if you were a little insect or an ant going around the circumference, so if you start at 0 and you go up to 90 degrees, or the equivalent of 90 degrees is pi over 2.
Mhm.
And then on this side, you have negative.
Negative pi over 2?
No,
Negative
not
pi.
over 2.
I can't see. What is that?
What, here, you have 3 over 2 pi, or 270. In other words, I'm going around the clock face.
Oh, that's just negative pi.
0,
Okay.
yeah, 0 to 90 degrees to 180 to the other direction.
Because the diameter is 2, right? That's where you're getting, that's what, it's because the diameter is 2?
No, this is for all circles.
Okay.
Now, what I'm doing is I'm getting back to 0, but if you go all the way around, you don't come back to 0, you come back to pi. And if you keep that self-similar spiral action, and you don't expand, if you don't expand the radius, you get a cylinder.
Right.
So when you come back to the origin, instead of 0, it's pi, 2 pi, 3 pi,
Oh, yeah, one way around.
and so on. So getting back to the light ray. So if you have this circular action, and if you have continuous circular action on a cylinder, you get sine wave,
You get a sine wave.
right? Just from 0 to 1, 0, back to -1, continuously. Now, a light wave ray consists of 2 components, both a vertical component and a horizontal component. Now, I don't have a video of that, but I can use my arms here.
Towards me. Forward. No, right there, right in front of you. Right here.
Okay, I got that.
Yeah.
Right. So if you're looking at the light ray coming at you, you have electrical field and a magnetic field coming at you. Now, the polarized light, if you look at just a polarized light and the x-axis being 0, if you tilt it then it's polarized to the right. If you tilt it to the left, it's polarized to the left. And I can get back into that. But if you go from cylindrical action to increasing the radius, like we did last week with Brian, with the conic sections, you get, instead of a cylinder, you get spiral action. And you go from the arithmetic mean to the geometric mean, and you continually have growth. And what LaRouche has used is conical spiral action to show growth in a human economy. And if we remember last week, we had the connection of growth along the spiral by means of the elliptical function, which I think you had that as the fourth. But first, can you put up the first
Sure.
slide?
Someone could clean the board off there. Yeah.
I think there's
No, she's, it's right in there.
Oh, in here.
Yeah. Sorry. Thank you. Okay.
Okay.
All right.
Okay, which one did you put up?
I put up the one you just drew with the 1, -1, square root of -1, negative square root of
Now
1.
does it take both of these?
You should still watch out, Joel.
Clear?
Clear.
Okay.
Okay, so I think the circle of the slide is a little more perfect than my circle.
Only a little.
Only
Just-
slightly.
Just a little bit. All right.
Yeah.
So this is your complex domain. Now, for every number on, is this the diameter?
Yeah, there's the diameter right there, and that's the right-hand side of it. So it's going to
Okay.
across the,
So if you were to take a number on the x-axis of the number line, every number is a complex number. But if you have no y component, then all you have is the x component. So in other words, I'll just put it out here. So every number is equal to x plus iy. So that every number in this circle,
X plus IY.
right, I being the square root of -1. So if you have a point in the first right quadrant of the circle, it would be, say, if it's right on the circumference, it'd be 1 plus the height of y. So it would be 1 plus I y.
She's gonna give you a dot.
yeah, Keisha's going to put a dot on the circle there.
Oh, okay.
Okay.
Wait a minute, I'm
Hold on.
I can't see it. Okay.
There it is. Okay.
You can't see it. So when somebody says, well, this is a complex variable, it's a complex number, all it means is you have a x component, and to represent the vertical axis, you have a, say, if it's 1i or 2i, you have the vertical component. Now, so this is the complex domain that Gauss mapped out. Now,
What is the I, I'm sorry, what does the I represent?
okay, the I, if this is a unit circle, a circle of radius 1, then from the center of the circle to the very far to the circumference is 1,
Okay.
0 to 1. From 0 to the left side is -1.
-1.
Right, so the average is 0. the geometric mean is the square root of -1 times 1, which is the square root of -1, which is known in mathematics as the imaginary. Although Gauss showed that it wasn't an imaginary, it had a physical significance. So when you say I, it means that you're going up the vertical y-axis. And then if it's a bigger circle than just a unit circle, then you have I or 2I or 3I. And then you can use that to map out your complex numbers inside the circle. So that's just what is called a complex variable. Now, if you remember last week, we went through the conic sections. Now, could you show the second slide?
Yes.
Shall we erase what you had?
Yeah, I'll get it. Oops. Yeah.
You got it.
You need a self-erasing.
Yeah, we need a self-erasing board.
Okay, so which one do you have here?
That's the one that's the two circles, one inside the other, and you've got a z and a z squared angled from the z is on the first circle, and
Okay, coming out.
yes, two concentric circles.
Two arcs.
Yeah, z goes to the first circle, and z squared goes to the second circle.
Okay.
And then there's an x and a y arcs that map the angles.
Okay, now I'm going to the third conic
Okay.
section.
Okay, got the conic, got the ellipse cut out of the conic section.
Okay, now is the apex up here
Yes,
at the top.
yes.
Okay,
Yeah.
so what LaRouche uses is that if you take a circular cut across the cone, so you say that circular cut represents the current state of your technology or your current platform. So if you think of the first circle, that would be like your wood burning technology.
Now, do you want the circles right now, Joel?
Yeah, it's got an
Why don't I,
there now.
yeah, it's got.
Oh, it just has the ellipse?
Yeah.
Okay, well, if you imagine, if you take parallel to the base, does it have a
Okay.
base down here?
Yeah, there's a base.
Okay, just imagine a circular, not an angle cut,
Yeah,
but a
there's a-
circular.
okay.
Circular like that. That.
Yeah,
Okay,
Okay.
Melinda, should that, Melinda?
Yeah. Oh, yeah. So, we've got the base, and we got, let's see, the bottom of the ellipse, and the top of the ellipse.
Okay, does he have a number A and B?
No, you want me to put an A on the
Okay.
bottom and
Yeah,
then
put an A on the top
on the top of
and then B.
the circle. Okay, top circle.
Right, so if you think of conical action, your first cut of the cone would be your level or your platform of technology, like wood burning or charcoal. You make a discovery of a physical process that gives your society more power over nature. So if you make a discovery and you discover how to use oil and gas, you go to a higher density of energy. And so your effect on the universe is larger. So you can go from circle A to circle B, or the B platform. And you continue to make breakthroughs, because if you stick at one level of technology, you'll use up that resource. And eventually you can still get wood, you can still get oil, but it takes more and more intense searching to get the same amount of energy. So you're actually, if you keep at the same technology level, you will not consume all the resources, but you will begin a death spiral, the megatropic collapse of your economy. So you must always have an expanding body of technology and physical principles that you can use.
You said negentropic collapse or
Right.
entropic?
Entropic. Yeah, not megatropic, entropic. So if you look at a physical economy, you go from wood, charcoal, to oil, gas, eventually nuclear, and eventually fusion. If you're not going up or expanding your cone of activity, then you'll reach a point where you will no longer be able to sustain that level, and you begin an entropic collapse. Now, the last slide, I want to show an example of what Edward Teller developed to get the first thermonuclear reaction on Earth. Now,
DH bomb.
Oh, sorry.
is that the fourth?
Yep.
Yeah, it's there.
Just
Now,
erasing the
are there any North Korean scientists in the audience?
No North Korean
They're
scientists,
probably
okay.
wiretapping.
If they are, you have to close your eyes, because this is still top secret. No, this is just the most outrageous example of negentropic growth that I can think of. So if you know the basis of an atomic bomb, so you just think of it, we've mastered oil, gas, then we discovered the nucleus. And in the early 20th century, you had key scientists who said, yeah, well, we can get energy out of this, but we will never be able to willfully get energy out of the nucleus. It's just impossible.
Who said that?
Rutherford,
Oh, okay.
Ernest, a British New Zealand scientist, he's the guy who was credited with discovering the nucleus of the atom. He knew from the work of the Curies, Marie and Pierre, and a whole string of scientists in the early 20th, late 19th century, that there was something coming out of a small piece of matter. What they were looking at was radium. And radium was decaying. Although if you measured your sample day to day, you would have the same weight. But it would be heating up and producing heat so that it seemed like it was the equivalent of tons of coal was burning. It wouldn't explode, it was just really extremely hot. Now, so over the beginning of the first few decades of the 20th century, through various experiments, and most of the experiments was you take a nucleus, you know what you have in the nucleus, and you shoot neutrons at it and see what happens. And eventually, in the 1930s, I went through this during Keisha's birthday celebration. A woman physicist, Lisa Meitner, discovered that what her colleagues who were still in Germany, what they were attempting is to make a bigger nucleus by bombarding it with neutrons. And instead of getting a bigger nucleus, it ended up splitting the atom and getting a large amount of energy. But he wasn't looking for that, so he was looking for a bigger nucleus. So he sent his papers to Lisa Meitner, and she said, well, what's happening is that you're splitting the atom and you're releasing a large amount of energy according to what Einstein had predicted back in 1905. And if you convert a small amount of mass, you get a huge amount of energy released. Now, for the Manhattan Project, this is the first Manhattan Project. They got us the atomic bomb.
Straight ahead.
Straight, yeah.
What they did was they purified the uranium so you would have a certain isotope concentrated. uranium-235. Now, to get it to explode, you have to reach what's called critical mass. You don't want it to explode in the belly of the plane.
No.
So the idea of the bomb was you had two cores, and over your target, you ram them together, and you reach critical mass, and you detonate. Now, the first bomb, both at the Trinity.
That's the map. Go to your left.
Further,
Go to your left.
further
John-
left, further left.
Yeah, there.
There you go.
Okay, and you're to the right of the picture, so that,
I got it.
yeah.
There.
Okay, just to give you an energy release of the first atomic bomb is in the range of 10,000 tons of TNT. Now, if you've ever seen the bombs that we dropped on Iraq and Syria, they're typically 1,000 pounds of TNT. So 1,000 pounds would drop on this building, would take out the whole block. So if you think of that, and you double it to get 2,000 pounds or 1 ton of TNT released, and then you multiply that 1 ton by 1,000 or 10,000 times. So imagine you have that 2,000 pound bomb and you multiply it by 10,000 times the energy released. That was the first atomic bomb in Hiroshima and Nagasaki. They were 10 to 20 kilotons. Now, Teller and other scientists knew that besides splitting the atom, we could also get energy from fusion. Now, they knew that fusion was what was occurring in the sun because they would take readings, spectrographic readings of the sun, and they detected an element helium. Now, the most abundant element in the universe is hydrogen. So they had to figure out, well, how does the sun stay warm for billions of years, and how does it produce helium? Well, it produces helium by fusing the smaller atom, the nucleus of hydrogen. Now, what Teller figured out in the late 40s is that we can use an atomic bomb to create a larger explosion in the hydrogen bomb. Now, the difficulty is to recreate what occurs in the sun, the fusion of the sun. The sun has a huge mass that squeezes the element hydrogen together, and it has such a huge mass and such a high temperature over such a long time that you get enough fusion that the sun fuses every second something like 600 million tons of hydrogen every second. And it takes years, some say 100,000 years, for the energy produced at the center of the sun to eventually make its way to the surface, and then 8 minutes to get to Earth once it's at the surface.
Wow.
So the idea was, well, we can't reproduce the sun's mass on Earth, but what we can do is we can have a temperature of millions of degrees to trigger the fusion. So that's why it's called thermonuclear, because you first have to have the large heat, and then you can produce the fusion, which gives you more energy than just splitting the atom. So what Teller figured out is that is the ellipse up there now.
Yeah, it's to your left. I mean, yeah,
Once the
keep
ellipse.
going. Oh,
Okay.
the ellipse of the hydrogen
Right,
bomb.
the
Right.
H bomb. So what Teller figured out is that the problem is if you just detonate an atomic bomb around the glass full of hydrogen, deuterium, and tritium, what will happen is it will heat up to millions of degrees, but the blast will blow your target away before it has time to fuse. So what you have to do is use the geometry of the ellipse to first detonate the atomic bomb, which then spews out not just heat, but X-rays onto the surface of what's called the chamber, the hull chamber. And I think it shows the arrows, the hard X-rays.
Yeah.
Those are high energy X-rays, which are then re-emitted at a lower frequency onto the other ellipse. So you have this ellipse with the foci having the atomic bomb, the trigger, that detonates. It sprays X-rays inside the chamber, which are concentrated with equal pressure to this target, which has your hydrogen, your deuterium, and tritium. And it compresses that so that the compression is equal all around. So it's isoperimetric all around. If you don't have equal pressure on your target, it'll just blow away. So once you concentrate that energy onto the target, you fuse, and just to show you the increase in power. So your atomic bomb has 10,000 kiloton equivalent of energy release.
10 kilotons.
Yeah, 10 kiloton. A kilo is 1,000.
Yeah, right, okay.
So he triggered that, and because of the design of what Teller came up with, the first hydrogen device with 10 kilotons, or the 10 to the 4, it produced an energy release of 10 megatons, or 10 to the 7.
Wow.
So it increased the output by 3 orders of magnitude.
So what's with hard X-rays and soft X-rays and metal foil, or, you know?
Right, you see, if you just have the hard X-rays, those are what are emitted by the blast, the atomic blast. Now, hard X-rays, it simply means that it has a higher frequency. They're more energetic. You have to reduce the energy of each X-ray photon by interacting with the foil of the chamber. And it downshifts the frequency of the X-rays to what's called soft X-rays. It's just less energetic. But because it's less energetic, it is able to compress hydrogen to a high enough compression in temperature that it will fuse. And once it fuses, it releases 1,000 times more energy than what you put into it. So this was proof that we could create thermonuclear reactions on Earth. Now, the only problem is you don't want to release 10 megatons of energy every second.
Mm-hmm.
So what they're doing now at Lawrence Livermore is they're using lasers in a similar chamber to shine lasers onto what they call the hull room, the chamber, and generate soft X-rays that will compress a small tablet of hydrogen, deuterium, and tritium to get, instead of 10 megatons, say you would get out 1 kiloton in a chamber which can be contained And then all you have to do is be able to convert that to drive a turbine. Now, if we were to, instead of using deuterium and tritium, if we use helium-3, then we get the explosion is charged particles, which we can then use to convert directly into electricity. Or we can use to heat up propellant to shoot out of the backside of a rocket as your propulsion.
Right.
So this is what is being worked on.
Can we do the lights, Joel? Are you
Yeah,
gonna do
yeah.
this? Okay.
Is there a reason that it's shaped in an elliptical shape? Is that important?
Yes. Yeah, because of the ellipse, so that once you detonate something at one foci, it will concentrate on the other foci.
Oh, I see. Yeah.
Because if it was just a cylinder, right, so if it was just a cylinder, you would just generate heat,
Yeah.
and you wouldn't get
Huh.
the equal compression of your target.
Huh.
So this, using conic sections and the complex domain, Teller and his colleagues, and again in the late 40s, people were telling Teller that we could never get fusion. It's impossible that the blast from your atomic blast would be so intense that it would blow away your target.
Yeah.
So he used the ellipse so that the energy of one foci is concentrated on the other.
Wow.
But the experiments they were doing in New Jersey, in Princeton, were with a toroid.
Right, that's a different type of, the problem with the torus is that what they do with the torus is that they input so much energy into this hydrogen gas that it becomes a plasma. Now, the plasma separates the nucleus from the electrons. And the problem with that is that plasma it's not very dense, but it's very hot. It's millions of degrees. So if any part of that plasma touches your torus, it cools off
The containment vessel,
the
you mean?
containment vessel.
Right.
Right. So the way you contain that plasma is with magnets, both toroidal magnets and circular magnets. And what they've been attempting is to increase the density, the temperature, and the time that those conditions can be held inside the magnets, so that you can have the fusion of the hydrogen, deuterium, tritium. And once you get that fusion, the problem they've had with the torus is that it takes more energy to run the magnets than you get out from the plasma, from the fusion. So that's the problem with the magnetic confinement. Now, if we were spending more than $300 million a year on fusion, magnetic fusion research, we would have probably figured it out.
Yep.
How to do
30
that.
or 40 years ago. So I wanted to use this example to show that we can get thermonuclear fusion, we just have to be able to control it better. But if you look at just the release of energy from atomic to fusion, that's a type of leap that if you can control that it would revolutionize your entire economy, your entire society. So I think I'll leave it there, but I wanted to use that as an example of what Lynn is getting at with his complex domain and the self-similar spiral action and the elliptical functions. Try to give it a physical meaning in the universe.
When you say plasma, can you define that better?
Right, so you're breathing a gas. The air, this is a solid. If you have a glass of water.
I do have a
Yeah.
bottle of water.
All right, well.
Do you want it to drink?
Well, it's just a liquid, just
Okay.
to give you an idea.
That's liquid.
So you have solid, liquid, and the gas in the air is gas. The plasma is gas heated to over 10,000 degrees. So that the gas in the air is normally nitrogen and oxygen, trace amounts of CO2. And there are molecules of the elements like H2O or CO2. And the electrons are bound to the molecules of the elements. If you heat it over 10,000 degrees, then what happens is that the molecules become so energetic that the electrons of the molecules of the elements are stripped. So that while the air is neutral, because each nucleus, which has a positive charge, has an equal and opposite number of electrons. So that the positive and negative cancel out, so you have a neutral molecule. If you heat the gas into a plasma, then your plasma has a charge, so that your nucleus is positive, your electrons are negative, and they can be controlled in a magnetic field. Now, if you look at most of the matter in the universe, it consists of plasma. Because you just look at our solar system, 99.9% of the mass, the visible mass in our solar system is in the sun. The planets, the moons are less than 1% of the mass of the solar system. Now the sun is a plasma. It's millions of degrees at the center and thousands of degrees at the surface. So that if you look at just our solar system, most of the mass is in the form of plasma. So that's what a plasma is. If you look at your fluorescent lights, there's some kind of a mercury vapor in the fluorescent light. That's why you don't want to drop them and blow up.
When you say the electrons are stripped, you mean the electrons are separated from the nucleus? Is that what
Right.
you meant? Okay.
Right. The simple way, if you think about hydrogen, it's just one proton orbited by one electron. So it's neutral.
So the electron just goes and flies away? What does it do?
Right,
It stays in the plasma
it's-
area?
Say if this was a hydrogen atom and I heated it, the electron would leave its association with the
That
hydrogen,
hydrogen.
and it would still be in the room,
Mhm.
but it would no longer be associated with
With
that
that
nucleus.
proton. Okay.
So it doesn't disappear, it just is no longer
It's
tied.
free flying all around.
Could
Right.
you take that to the level of the magnetic retrieval of elements with the fusion torch?
Yes. Right, good. This is how a lot of the elements were discovered, is that if you heat up a plasma and you run it through a magnetic field, the lighter elements will travel more than your heavy elements. And so you can actually separate the various elements just by fractional distillation. So that it'd be like if you have a race with a 200-pounder and a 100-pounder. The 100-pounder is twice as far along as a 200-pounder. So you can separate the elements by mass because they all have a positive charge. The bigger mass has a bigger charge, but you can separate it with the magnets.
So how hot do these elements have to be for it to be separated out?
Typically about over 10,000 degrees.
What is that, when you, could you also define toroidal? Is that elliptical?
Donut.
Right, well,
Toroidal. So
you see, you got pie,
Donut.
and you have donuts.
It's traveling of the, I mean, to make the donut, it's something traveling around and shaping itself in a donut in the path it's taking. Is that what you mean when you say toroidal force?
Well, what you do is you place the magnets around. You have a chamber, a metal chamber, and you place the magnets around. If you take a cylinder and just segment it, so that if you have enough segments, you can make instead of a square, make a donut. And you place magnets along the north, south, and horizontally to control the plasma, so it's spinning inside. It's a hollow donut. That's called a tokamak, because that tokamak is donut in Russian. I'm sure Kislyak has a lot of donuts.
You know, I mean, maybe it's evident to everybody, you know, from what you presented. But I think if you take what Lynn is saying about what we have to do to shape this new administration, you know, that, I mean, this is just so clear because, you know, you think of what Trump laid out in the inaugural address. You know, there is no way, you know, in the universe that he's going to be, he would be even capable of carrying out what he talked about in terms of the physical transformation of the country.
Talking about the address on.
Oh yeah, I'm sorry, the State of the Union address. That there's no way he could carry that out without, I mean, there's no way we don't even have an electrical grid that can keep the lights on in Texas or in half the country in a cold wave or a heat wave. So, you know, we don't have the power grid. We don't have the power sources right now to even be able to have a broader infrastructure base at this point.
Right. Well, if you think of the code.
Yeah.
So he's saying that we have to keep going around the circle faster. So think of fracking. You know, it's a new way of getting an old fuel.
Right.
So you have to spend money to frack and do horizontal. Now, if you keep in that same mode of production, then eventually it's going to take more money to frack than you get from the gas.
Right.
So while Trump wants to increase the circle, unless you expand the circle, make a bigger pie.
Right, bigger base of resource.
And the only way you do that is through new discoveries that give you more power per gram of fuel.
Mm-hmm.
So that you're right, if you stay in the same platform, like he was on the nuclear carrier,
Mm-hmm.
Gerald R. Ford, the
Right.
biggest carrier.
You can have that water if you want it.
It's nuclear powered and all that. But it's the same type of carrier we were producing 40 years, 50 years ago.
Mm-hmm.
There's no breakthrough.
Mm-hmm.
So that if all you're doing is improving on your current mode of production or current technology, then you get a nice bigger car or bigger carrier, but you're not going to get to the moon with a carrier.
How do you-
What, I was just gonna say, one of the things you suggested earlier, when you said you can use a fusion energy to get a more dense energy, and then you can convert it into electricity. But one of the things you implied, if you had this polarized electronic field fusion, then rather than converting it like we've been doing all along, you take that heat and you turn it to a generator to produce electricity, you can take the electricity, as you were suggesting, right off the plasma. And I guess
Right.
the rates at which you get electricity are even higher than also.
Right, because like that carrier has a nuclear engine. And what it does is you surround the nuclear reactor with water under pressure. And the water under pressure, you can get to be 600 degrees Fahrenheit. And it's that water under pressure is used to heat a secondary loop of water that can turn into steam, which then turns the turbines, which then either turn the screws or it feeds an electric motor to run the carrier. Now, the energy you begin with the nuclear reaction, by the time you heat the water and transfer the temperature of the water to the turbine, you get out about 40% of what you put in.
What you started with.
So it's 40% efficient. So if you were able, through using the plasma, to use the charge of the plasma directly without boiling water, then instead of 40% efficient, it could be 70, 80% of your energy is converted to electrical power.
Is this like the magnetohydrodynamics?
Right. That's what it's called. Yeah.
Mm-hmm.
What is when you talk about and this is a little off the subject, but I'm just curious about, I can't even fathom heat going above what, hurts my finger when I touch the stove water. I mean, how could heat get to thousands of degrees? Just what kind of energy does that, and what exactly is heat? I mean, can you define?
Well, heat technically is the motion.
The friction?
Motion
Mm-hmm.
of atoms. If there was no motion on your molecules, if there was no motion, then you would have absolute zero.
Huh.
So if you think of your freezer, you have the ice cube. The ice cube is made of water, which is the same molecule as your tap water. But the difference is, in your freezer, the energy is taken out by the refrigeration cooler, so that the molecules in that ice tray are moving so slowly that they can make a cubic crystal ice. Now, if you take that ice tray out of your freezer and just leave it, not on the stove, but on the countertop, the room temperature is so much more energetic that the crystal form breaks down. But it's the same molecule.
Wow.
It's still H2O.
But it's moving.
But it's moving so that you no longer have a solid crystal, but you have a fluid. Now, if you put that water from the tray and you put it on your
Stove.
firmly in a pan or something, or a tea kettle on the stove, then the element, your heating element, excites the molecules further, so that instead of a fluid, it becomes a gas. So they're separate. So the heat is just the movement of the molecules.
Does having things going slowly make them come together, and is that why cold is heavier? Cold air is heavier and hot air
Yes.
is lighter?
Right. Although it could be tricky because if you look at ice floats on water. So ice, because of its crystal nature, is lighter than water.
Wow, even though you think it's more dense or something.
Right. So if you heat something up to a gas, and then you continue to heat it, now there's a limit to how hot you get with chemical reactions. So if you go to another level, another circle in the conic section, then instead of just a chemical reaction, you get a nuclear reaction, which is millions of times more energy than just chemistry. So that inside the sun, because of the fusion going on at the center of the sun, it provides the heat in millions of degrees, and that heat is then turned into electromagnetic radiation, which we see in the form of light. So heat is just the movement of the molecules. Now, the other thing is if you get a star that's reaching the end of its life, so you have a fight between the gravity, which is compressing, and the fusion, which is expanding it, so they're in equilibrium. If you lose your fusion, then the star will collapse on itself. And if you have enough mass, it could explode as a supernova. And the temperature of a supernova is in the billions of degrees. And we've actually used lasers and hit targets in a vacuum where on Earth we can generate 100 billion degrees in a chamber. Now, that's a very low density plasma.
So fusion is when the molecules are coming together. Fission, is that the opposite?
Right, when they split.
When they
Now, it's not the molecule, it's the nucleus.
The nucleus, so that term refers specifically to the nucleus.
Right.
Okay.
Because a molecule is something like H2O. So you have hydrogen and oxygen sharing their electrons.
Right.
So that to fuse, you have to separate the hydrogen from the oxygen. And then the hydrogen nucleus comes together with another hydrogen nucleus and creates a new element, helium.
And the isotope you're referring to is when you add neutrons to that atom, right?
Right, that nucleus.
To make it heavier, the nucleus of whatever atom you're talking about.
Right. Now the word, if you remember your periodic table, you have your elements. And each element has different isotopes. Now, isotope means the same place.
Does it have a limited amount as to how many neutrons you could cram into a thing?
Yeah.
That'd be interesting. I mean,
Because at a certain point, like uranium is the highest density of protons and neutrons in the nucleus in a natural occurring element. And if you destabilize that nucleus with just one little neutron comes in there, and it can lead to the splitting of that whole
Really?
atom. So that uranium-235.
Wow.
So you think of hydrogen as 1 pound. So if this is hydrogen, one pound. So by the time I go up the scale of the periodic table to uranium, I have 92 pounds equivalent in the nucleus, but that's just protons. On top of that, there are 146 neutral, what they call neutrons, in the nucleus. So the nucleus of uranium, that's why have you ever had depleted uranium? You have depleted uranium?
No, I don't.
Well,
Heard of it.
they use them as bullets. This is what freaks out.
Yeah, it's all over Iraq, right?
Right, because
Oh, depleted uranium.
well, we used to use depleted uranium. We had an infrared sensor, and it was a big pod that had the sensor on one end, so you could look for targets and stuff. And at the tip of this pod was depleted uranium, so you could balance the pod on the airplane. So the tip was 240 times denser than water, because it had uranium as the metal.
Huh.
Now the advantage is if say this was the tip of a bullet and it weighed 1 pound. Now instead of just 1 pound, if I replace it with something that weighs 200 pounds, but takes the same area, and I'm able to shoot it from an airplane, then once that 200 pounds hits a tank, it goes right through the steel.
Yeah.
Now the problem is it vaporizes inside the tank. And the danger is that then you have all this metal that you can inhale.
Breathe.
Yeah, wow.
And so you die from the heavy metal, not just radiation.
Whoa.
That's what anti-tank weapons are?
Yeah. Well, the one I'm familiar with is the A-10. It's this ground attack jet that has a Gatling gun on the nose, and it just fires like 100 rounds a minute.
Shoot.
This is what they use in Iraq,
Great.
Afghanistan. So it's not nuclear, but it has some very bad effects.
Yeah.
Now they've actually you can smash other nucleus onto things like uranium, and you can get bigger nuclei, but they only last a few seconds, a few microseconds.
Those are the transuranic.
Right.
That's a lot of elements. It's like 20 elements or something?
Well, you have one in your smoke detector. It's called americium, and it's from nuclear reactors.
Really?
But yeah, you just look at the back of your
They have a
fire.
warning on
There's
there.
nuclear waste in your smoke detector.
Well, don't freak out, because what it does is it's a man-made element that has a half-life of something like 700 years. So that if I start out with a pound, in 700 years, it'll be half a pound. And it'll decay into something else. Now, when it decays, it doesn't split. It shoots out helium nucleus, or what they call alpha particles of 2 protons, 2 neutrons. So that if you use that stream of particles as a circuit, that if the smoke particles get in the circuit and block that stream of alpha particles, then your detector detects that there's a blockage and says, well, there's a smoke detector.
Let's create a real problem for the greenies.
Right, well, after September 11th, the Department of Homeland Security actually paid for a study to see how many smoke detectors would it take to make a dirty bomb.
Oh, God. And what did they decide?
It'd be like tens of thousands. It's just a few
It's
grams.
suspicious that somebody's gathering a bunch of smoke detectors to call the home.
Yeah, right.
Selling, you see, we buy gold, we see, we buy gold. It's
Well,
suspicious.
actually, you probably get more radiation from bananas because it has the potassium. And potassium has a radioactive isotope. And that's why each person who's alive has radioactive isotopes. And the bananas will trigger some of these radiation detectors at the ports.
They will?
Yeah, because it emits
You
radiation.
mean they try to detect radiation on the ships coming in and some of them are bananas?
Right. And sometimes they detect, a dirty bomb of bananas.
It was just cocaine, right?
Okay. I think I'm gonna stop the broadcast.
Okay.
Okay.